Okay, so today we're going to look at two major applications of matrix algebra, and they're both kind of cool. Now, if you've ever had statistics, then you are familiar with the concept of linear regression. Now, this is not polynomial curve fitting. We showed earlier that if I give you n data points, each with different x coordinates, that's critical, there's exactly one polynomial of degree n minus 1 that passes through every single one of them. Now, linear regression is quite different. The concept with linear regression is something more like this. I'm going to give you a whole bunch of data points. You know, I'm going to give you a lot of data points. Hopefully you guys can see that. I got a lot of dots on the board here. And the idea is there absolutely is a line that exists that is closest to all of these points simultaneously. And part of the goal is to calculate that line. Now, that line is probably not going to pass through any of the individual points. So how do I decide what's the best line? Well, let's just say, first of all, I notice that these go uphill. So there's something called correlation. Now I'm going to use a few statistical terms, but we're not going to do any of the statistical calculations. The concept of correlation is how good of a predictor is the input for the output. So if I'm just filling up the entire XY plane with dots, then there's really no predictability. But if my points lie very close together, or in other words, if there's a line that all of the points are very, very close to, then we say they are highly correlated. If they're kind of random all over the place, we'd say there's not a lot of correlation. Now, if the points go uphill from left to right, then we say the correlation is positive. If they go downhill, the correlation is negative. Now, perfect correlation would be 1. Perfect negative correlation would be -1. And absolute randomness, no correlation at all, would be 0. Now, you have to understand that in reality, it's virtually impossible to get a correlation of 0. Here's the only way I can get a correlation of 0 is if I threw n data points on there and they perfectly form the vertices of a regular polygon of degree n. In other words, I give you 4 points, perfect 4 corners of a square. I give you 8 points, perfect 8 corners of a regular octagon. That's one where all the angles are congruent and all the sides are congruent. In other words, I see a perfect circular pattern forming. That's it. That is the only mathematical way to get a correlation of 0. So if I said, all right, I'm going to put glue all over the board, you're going to grab a handful of sand, and each grain of sand is going to represent a data point. And you're going to throw the sand at the board. Yeah, maybe 200 little particles hitting the board. I am still going to see the illusion of correlation. I'm going to see an uphill or a downhill trend. What I'm not going to see is a perfect circle being formed. That's basically impossible. It's a 1 out of infinity probability. So in other words, it is virtually impossible to get a correlation of 0, even if you just are completely random. I'm just going to make up a bunch of points. No, if I just said, I'm going to throw 3 darts at the board and I'm going to close my eyes. Those darts we know are either going to line up perfectly, in which case, wow, that's my line, or they're going to be triangular in nature. Probably more triangular, but then there's still a really obvious simple line that I can draw. So we're going to make one simple assumption. We're going to start with data points where we already have reason to believe that there is correlation. That's based on previous stuff. That's a statistical thing. We believe there's actually a cause and effect going on here, okay? We're not going to prove that. That's pure statistics. It's valid, it's important. We're going to just concentrate on the mathematics. So if there is a line of best fit, let's say it was this one right here. I said before, it's very unlikely to pass through any of the points. So what we do is we take every point on the line, and we usually use, we write it this way. We say y hat, that's my line of best fit based on my data, is equal to a0 plus a1x. Now, we write it kind of backwards. You say, don't you usually put lines in descending order, right? Don't you usually put, mx plus b? Yes, but understand from a statistical point of view, regression can have multiple variables. I can have a lot of variables. So we usually think of it as constant a1, x1, a2, x2, a3, x3, all the way up to an, xn. I can actually have n independent variables. It's still linear because they're all first power. So if you're taking an upper level stats course, you're doing regression analysis, you're going to deal with lots of variables. What we do in our case is we're going to say, no, let's just assume there's only one independent variable. So since this equation would just keep going, we just chop it off and we're only going to look at this much. That's part of the reason that we write it in this order. It's not wrong to reverse the order, not at all. Y hat would be our measured. The X values are given, the Y values are given. But on the line of best fit, I'm still using the same X values, but I'm trying to estimate the Y values that are on the line. So what we do is, here's a point and I'd go up to the line. Here's a point, I'd go down to the line. Here's a point, I'd go up to the line, down to the line. So all of these points would have a vertical distance from the line. The line of best fit is the line that minimizes, not the sum of the distances, the sum of the squared distances. That's why you've sometimes heard the term least squares regression line. The idea is the vertical distances I want to minimize, but that means if I have an outlier, something that's really far away, that's going to force the line to move. We really don't like outliers. So in general, the line of best fit is the one that minimizes the sum of the squared distances. Since it's unlikely the line passes through any of the X values, that's why we say we're predicting the line, but we're still using these X values, okay? Now, with that said, what the line of best fit is going to look like, okay? I'm going to write it like this. I'm going to give you n data points, okay? X1, Y1, comma, X2, Y2, comma, all the way up to Xn, Yn. Now, this is how we started the polynomial curve fitting problem. The difference in the polynomial curve fitting, first of all, I cannot repeat any of the X values. And secondly, we are finding the polynomial that passed through every point. Totally different goal now. Now I'm trying to find the line that is the closest to every one of those points. And X values can be repeated. Okay, there's no problem. The only time we will not be able to complete this problem completely is if I use the same X value for every single point. Now think about that. If I use the same X value for every single point, that means the points would line up vertically. So I wouldn't be able to calculate a slope. But if I give you n data points that all use the same X value, then I think it's pretty clear that X equals a constant is my line. That's not an interesting problem. So we'll assume that not all of the X values are the same, that I actually have some variation in the X direction. So what I want to find is that line of best fit. So I want to find a line that looks like this. A0 plus A1X equals Y. Now, when I do this, I'm going to get a system of equations. In fact, what I'm going to do is replace the X and the Y with these ordered pairs right here. So the first one would look like A0 plus A1X1 equals Y1. Then A0 plus A1X2 equals Y2. All the way down A0 plus A1XN equals Yn. Okay. Now, there cannot be a unique solution to this problem simply because I have n equations and the only unknowns are the A's. Remember, these are given. The X's and the Y's are constants. They're values. They're no variables. So these are not variables. These are numbers that are given. The unknowns in the problem are the A0 and the A1. The coefficients in my line are what I'm trying to discover. So I have two things that I'm trying to discover. I gave you n equations. There can't be a unique solution unless every one of these points was actually on the same line. Again, highly unlikely. So what we need to do is create a matrix product. Okay, so what matrix product would this look like? Well, how about if I wrote it this way? Okay, notice this is n by 2 times 2 by 1 So look at what I just wrote there. A0 plus A1X, A0 plus A0 plus A1X1, A0 plus A1X2, all the way down the line. That'll give me all these. And in each case, it equals these. So if you check this out and you perform the matrix multiplication, you will get this system of equations. Let's write this in the form, how about, we'll call this matrix capital X. We'll call this matrix capital A, and let's call this capital Y. Yes, Y is technically a vector. I've written my system of equations as a matrix product. My goal is to find A. If I can find A, then I'm done. Then I've got the coefficients and everything's wonderful. Oh, but we've been practicing this for the last week. All I got to do is find X inverse. Piece of cake, I think. Does anybody see a potential problem with finding X inverse?
It's not a square matrix.
Well, if I only gave you 2 data points. By the way, do we know this from remedial algebra that if I give you 2 points, there's exactly 1 line that passes through them? We know that. So assume that you probably have more than 2 points. Again, if you only have 2 points, there is exactly 1 line that passes through them, even if that line were vertical. Oh, but if I have more than 2 points and they're located all over the place, then there's no line that passes through all of them. That's what we're doing. So I can't solve this with a simple inverse because this is n by 2, and assume that n is realistically n is probably large. I mean, n might be 1,000. I can't find, oh darn. Well, how am I going to do this? Should I do row operations? No, that would take us forever. Remember, there's not going to be a unique solution. There's going to be a best solution. So I'm going to show you something really cool. We're going to come back to this in a moment. We're going to find something. We're going to find something called the pseudo inverse. Okay, we're going to find something called the pseudo inverse. I still want to solve this guy. Here's how we're going to do it. Now, matrix X, we know is n by 2. Tell me about X transpose. What will the shape of X transpose be? Anybody?
2 by n.
2 by n, okay. So if I multiplied X by X transpose, then I would get an n by n. And it's probably going to be absolutely huge. And by the way, it's square, but it will not be invertible. That's something I can't prove until chapter 4. But this is square, but it absolutely is not invertible. Okay. What about X transpose X? What's that shape?
2 by 2.
That's 2 by 2. Huh. And a 2 by 2 is usually invertible, except if the AD minus BC part. Well, it's actually fairly simple to show that if I do not repeat X coordinates, in other words, if I don't have all the same X coordinates, then this is absolutely always invertible. Again, some of the theory of this I'm going to prove in chapter 4. We don't have the theory all down yet, but this guy is invertible. Is that useful to me? Yeah. X transpose X, I have a lot of data points. This guy's too big, it's not invertible. This guy's really small and it is invertible. And it's also easy, it's 2 by 2. So what if you did the following? I want you to consider the following. I want you to consider X transpose X inverse, the inverse of that product. Besides, by the way, we know that if 2 matrices are square, we showed this last week. If I said A and B are square matrices, and A and B inverse exist, then we proved last week that this is always true. If A and B are both square and the inverses exist, we know this is true. X and X transpose are not square, therefore neither one of them individually has an inverse. That's not what we're saying. We're saying their product is 2 by 2, so I'm going to take the inverse of their product. Okay, not individual inverses, just the inverse of their product. So with that, imagine that, and then I'm sorry. Yeah, I've got this. Now, if I want to do this much right now. Hold the thought here. I just want to do that much for a moment. Leave the Y out for a second. We're going to multiply that one. This is 2 by 2. This is 2 by n. Okay. That means this whole thing right here is 2 by n. What if, remember our original problem was this, our original problem is xa equals y, and we're trying to solve for a. Just for fun, what if I multiply both sides on the left by this big icky quantity? What would happen? Well, let's see. On the left, I have x transpose x inverse x transpose, and now I'm going to multiply it by this, equals, well, down here, x transpose x inverse x transpose times y. That's the right side. Very, very busy on the right side, but don't look at the right side, look at the left side. Matrix multiplication, although not commutative, it is associative. So I can regroup this. So now on the left side, I have x transpose x inverse x transpose x a. That's my left side. That's interesting. This is a 2 by 2 that exists. This is a 2 by 2. What will the product of these two be? Anybody?
Isn't that an identity matrix?
Which identity very specifically?
2 by 2 identity.
2 by 2 identity. I'm going to write I2. On the left-hand side, I now have I2 times A. Won't that equal A? Wait a minute. We just said X inverse does not exist, but we just multiplied both sides on the left by something and we got A all by itself. This quantity here, X transpose X inverse X transpose, isn't even square, yet it undid this multiplication. So it acts like an inverse. That's why it's called a pseudo inverse. It's not a real inverse because it's not even square. Yet when I multiplied the left side by this quantity, I got the identity on the left side. So we just figured out a way to solve this problem, folks. This is a very, very powerful formula. So the formula that we just figured out was if I multiply both sides on the left by this, then this is the answer right here. So I will write it out now. We're starting the problem as xa equals y. We now have A is X transpose X inverse X transpose Y. And it's usually easier to think about it grouping in that manner. That's how we solve the problem. This will give us our line of best fit. And it's a very cool process. Now, those of you who have had statistics, you say, well, in statistics, we had to do things like the sum of the scores, the sum of the, the XYs, the X squares, the Y. You had to do all of these individual things. You had to put all this stuff together, and it was really, really long-winded and complicated. All of the linear regression formulas you have in statistics, every last one of them comes directly from this. In other words, it was derived using linear algebra, not using any form of statistics. It's kind of a cool thing. I've taught stats for years. I don't show this in stats because most students haven't had the math, but it's really, really cool process. So let's do a problem and let's find the line of best fit. So let's suppose, let me give you the data points. I've got, oops, where's my, hold on a sec. Oh, here they are, sorry. I wrote them down right here. All right, I've got 5 data points. I don't want it to be outrageous. So I have the points -8, -7, -4, -3, 1, 6, 3, 8, 6, 12. My personal preference is always to write it in such a way that the X values are increasing. I don't care about the Y values. I always like to do the X values increasing. And at some point, I actually do like to draw a picture because these are 5 random data points on an XY plane. I'm going to come up with the line of best fit. I'd kind of like to know, how close is my line to these points, kind of as confirmation that I did it correctly. So what we're going to do is we're going to first identify the 3 major matrices, X, X transpose, and Y, because I can't do the problem without that information. So the X matrix, capital X, is 1, 1, 1, 1, 1, and then the X coordinates, -8, -4, 1, 3, 6. Okay, this is how we defined it a moment ago, right? All ones and then those guys there, okay? X transpose, therefore, 1, 1, 1, 1, 1, -8, -4, 1, 3, 6. And finally, the Y matrix would be -7, -3, 6, 8, 12. Okay, got to get that right. Now, the rest of the problem is just going to roll off my pen, okay? So in order, the first thing I want to find is X transpose times X. So X transpose X, which I know now is going to be a 2 by 2 matrix. I'm going to go this way. It might be easy to write X transpose first. So my first calculation, I'm going to go boom, 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 boom. That's just 5. My next calculation is going to go this way, which means I'm basically adding these up. That would be -2. My next calculation is this row times this column, which is also -2. And my last calculation is this row times these values, which is 126. Okay. This plus this plus this plus this plus this. Okay. Now, if you've had stats before, this might seem familiar to you. I'm going to show you something because I taught stats for a million years, and I would use what's called summary data. I don't have people do all the little detailed, like, let's just collect data. What would actually go in here, N is the number of data points. You notice -2 is simply the sum of the X values. And down here, it's also the sum of the X values. This matrix is symmetric, okay? In other words, this looks like it's transposed, and we showed that the product of X and its transpose is always going to be a symmetric matrix. But what goes here? This would be the sum of the squared X values. And in statistics, you need to actually find these values in order to complete the calculation for line of best fit. In our case, we just multiplied them out. Next thing I need to do is find the inverse. That shouldn't be terribly taxing. So what we're going to do is first, let's rearrange the numbers how they're supposed to go. That's 126, that's 5, and then these two change sign. Now what goes in front? That minus that. So that would be, what, 630 minus 4. So 1/626. That's kind of ugly. Now, you can choose to wait to multiply the fraction, or you can multiply it in right now. It doesn't make any difference. So I can squeeze it in here. So I have 126/626. Here I have -2/626. I'm sorry, +2, sorry. And then here 2/626, and then here 5/626. Okay, that's my X transpose X inverse. For the purposes of multiplying by the X transpose Y, it's totally okay to perform this multiplication and then multiply these in. Might make it a little bit easier. The next calculation I'm going to do is the X transpose Y. So I'm going to multiply, boom, 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 boom. And that's going to simply be a 2 by 1. So when I perform that, it's this plus this plus this plus this plus this. So that would be 16. Then I'm going to do this, 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 this. So I did these ahead of time just to make it a little easier. That's 170. Now, just like the last one we did, what are these values actually? Well, it turns out 16 is the sum of the Y values, but 170, I multiplied the XYs. So we'd call that the sum of the X times Y values. So in a statistical sense, that's what goes into this matrix. So you could actually have summary data and just write it that way if you chose to, but we're going to leave it like this. Now, the last part of my calculation, the absolute last part of this problem is to take this and multiply it by this. So finally, I have X transpose X inverse X transpose Y. This is 2 by 2, this is 2 by 1, so this result will be 2 by 1. So when I multiply, and I use the fraction key on my calculator, I don't sit there and try to figure it out. By the way, don't convert to decimals. That's a bad idea. There's a There are a few very absolute but simple rules that apply across the board in all math and science that have never changed. You never, first of all, ever approximate a coefficient. You only approximate an answer. If we were graphing a line in baby algebra and your slope was √2, right? So your line is y equal √2x or something like that. You don't approximate the √2, it's √2. Now, if I need to approximate the y value, I would do it after I multiplied. If you approximate the coefficient, then every calculation has already been rounded off and it might be the wrong direction. Plus, what if your input was a √2? If you're approximating your coefficient, then you're going to get the wrong answer. You're not even going to get an integer. You can approximate an answer, not coefficients. You're finding the coefficients that go into the line. They're rational numbers. They're not decimals. If I'm calculating, it's always okay to express the answer as a decimal, not the portions that go into the answer. You never round off before you actually do the calculation, because then you're guaranteeing your calculation is further away, not closer. Round-offs don't get closer, they only get further. It's called accumulated round-off error. If you're an engineer, you actually take courses in this, studying just how bad an answer really is. So this is 1178 over 313, because only 2's will cancel. And this is 441 over 313. That's pretty ugly, but it is what it is. Now, I'm done with the problem, but I have not expressed my answer yet. My answer is in the form of a line. So I'm going to express the answer, and here's the answer. My answer is y hat equals, because I'm estimating. By the way, you say, well, why wouldn't you put an equal? If you've had statistics, it would make more sense to you. I have 5 data points. Does this represent all the data points that exist in the universe, or is this just a sample with 5 points? Remember, if there is an actual line, then there's an infinite number of points that are potentially usable. I have 5 of them. If I grabbed a different 5 points, I guarantee you I will get a different line. In fact, every collection of points will produce a slightly different line, because I'm estimating the absolute universal line because I'm only using a handful of points. It'd be equivalent to saying I'm going to measure 5 people at random on Mesa College to figure out the average height of a Mesa College student. Well, every collection of 5 people will give me a different average. And I'm using that average to estimate the entire population. I don't say that average is equal to the population. I said that's my estimation. So this, we say hat because it's an estimator. Now, that right there, the first number is the y-intercept value. So I write 1178 over 313 plus 441 over 313 times x. I'm not estimating the x's, I'm estimating the y's. This is my line of best fit. Now, is it a good idea to calculate these values as decimal values just so you have an idea? Sure, sure. This first one is about 3.76. The second one's about 1.41. Now, first of all, what is the whole point of using a line of best fit? Okay. Let me keep it really simple. All right, our company, let's say, has been around for a really long time. And every year we have a certain amount of production, and then maybe we have a certain amount of profit. And we've plotted it over the last 20 years. Our input would be production, our output would be the profit. And when I plotted it, I noticed, hey, you know what? Looks like we have fairly linear growth. So could I predict if our production is this value next year, then I could predict maybe our profit next year? Sure. Or I took randomly over the last 20 years, I just took a few of the years. What could I use this for the missing values? Sure. The rule of thumb with using linear regression is it's great to estimate anything between your highest and lowest x values. It's not great for predicting the future. If the last 5 years, this is how our company's done, then let me use this to predict the next 50 years. No, that's not how it works. I might be able to do it. If you give me an input, I can give you an estimation of the output, but you have to stay within the range of values you used to do this. You can't do this forever. So this line is the closest line that passes through these 5 data points. Now I'm going to give you the simplest check there is. I call it the quick and dirty. All right. It's very possible I made an error along the way. It's always possible that you made an error along the way. So how good is this information? Well, let's go back to this picture here. Let's take the 2 points that are the furthest apart. Now, I know for a fact the line does not pass through either one of those. But we know if I give you 2 points, there's exactly one line that does pass through those 2 points. So what is the slope of the line that passes through these 2 points? What is the slope? And I'm going to erase some of this stuff because I'm also going to draw a picture in a moment. The slope of the line that passes through these 2 points. Well, I know how to find slope, change in y over change in x. So if I'm looking at the two most extreme points, I'd have 12 minus -7 over 6 minus -8. And that's 19/14. Okay, 19/14. The line that passes through those 2 points has slope 19/14. As a decimal, 19/14 is approximately 1.36. Our line of best fit, our slope was approximately 1.41. That's pretty darn close. In other words, that gives me hope that I did the problem correctly, because the line that passed through my extreme points had a slope that was almost the same as my line of best fit. And similarly, if I said, what's the equation of the line that passes through here? I'm going to get a y-intercept that's actually very close to that number. That's the simple quick check, is take your two most extreme points and see how close the line is. Now I want to actually do a quick and rough sketch. You never have to do this, but it's always a good idea, if nothing else, to convince yourself that what you did was in fact correct. This is useful if you don't have a lot of points. Let's see, I think I need both directions here. So let's say about maybe like that. So I'm at -8, -7, maybe that's about here, and then -4, -3. I don't know, maybe it's about here, and then 1, 6, maybe about here, and then 3, 8, and then 6, 12. I don't know. This is not a perfect picture. Okay, this is my rough sketch. Now, my line of best fit is going to have a y-intercept right around here and a slope around there. It's going to be kind of this-ish, you know. It's not perfect, but you got the idea. My 5 data points lined up pretty linearly. There is no line that passes through all of them. In fact, there is no line that even passes through 3 of them. But there is one line that passes very close to all of them. Maybe it's a little above these 2, maybe it's a little below these 2. That's kind of how it works. Another way of thinking about it is, if I pick an x value, just pick an x value at random. Let me pick 3. Let me replace this x value with 3. Okay, 1178 plus 441 times 3. All right, 3. Oops. When I replace, oh boy, this is interesting. When I replace this x value with 3, this equation here gave me approximately 7.99 as a y value. My actual y value was 8. Whoa, that means this line passes ridiculously close to that value. By the way, again, that instills me with confidence that I did the problem right. So linear regression, why are we doing this? Because it's a really useful application of matrix multiplication. This is a simple matrix problem where all I had to do was find a 2x2 inverse and multiply a couple of small matrices together. Remember, x transpose x is 2x2. X transpose y is 2x1. So it doesn't matter how many data points I give you. The matrices I'm using to figure out the final answer are always going to be relatively small. So it's kind of a neat problem. Okay. All right, real quick. Does anybody have a quick question on, we're going to move on to something very, very different. This is just a really simple algorithm. So you definitely want to make sure you have the formula. On your notes in the module section, I do have some notes on this, you know, and then a practice problem, just sort of a general. In the textbook, depending on which book you have, hold on one second, because I think the 6th and, excuse me, the 7th and 8th editions differ slightly, I think, in terms of where everything is. So in the 8th edition, hold on. In the 8th edition, this problem is in section 2.6. I apologize. In the syllabus, it says 2.5. It's 2.5 in the 7th edition. It's actually 2.6 in the 8th edition. So I don't mean that to confuse everybody. I didn't realize that. I forgot that they had Yeah, they threw something else in there. So it's 2.6 in the 8th edition. All the information is exactly the same. And the author has lots of really nice little simple pictures. Okay. Now, the next thing we're going to do is not in our textbook at all. In the old 4th edition, let me pull one out here. Okay. Give you a quick, brief history here. Hold on, let me put myself again. I just lost myself here. Here we go. The first 3 editions of the textbook had 10 chapters. I used to teach chapter 10 back in the day, but it became fairly obsolete with more and more technology. A lot of the stuff we do, chapter 10, it's not that it's wrong, it's just obsolete and not very useful. We have improved methods. But chapters 8 and 9 are still extremely important. Chapter 7 is kind of the pinnacle of the course. 8 is the complex version of chapter 7. And then 9 is some really, really cool applications, what we're going to start today. So when the 4th edition came out, the publisher decided that the last 3 chapters weren't necessary to include. This came out about 2000. So the publisher decided the last 3 chapters weren't necessary, so they produced a book that had 7 chapters. Well, because I've been using this book since the first chapter, and because I'm actually a paid reviewer of the text, I complained and said, hey, I still teach those chapters. This is unacceptable. So what the publisher did, you guys see this at the bottom? They made a book just for me. This is a revised 4th edition where they put the last 3 chapters back in the book. This is the Special Mesa College edition. This I call the golden ticket. If you could find one of these, it's worth its weight in gold. This is the best one of all of them because it has all the chapters. Now, because basically Mr. Brown was the only person on planet Earth who was using those chapters, every edition that came out after this, they went back to just 7 chapters, and they put the rest of the chapters online. Okay, so I'm going to show you something. This is actually ridiculously simple to find. If you go online, you type in simplex method Larson linear algebra. That would be the safest way to do it. Now, on my computer, I get to SIM and it already gives me this. This is all of chapter 9 and chapter 8 are online. They're not bootlegs, they're not illegal. The publisher put these online for free, anybody. Okay, this is the actual textbook. This is what it looks like. It's really long-winded. The author takes a long time to explain every single step. So yes, you can go to the textbook to get the information. It's probably more useful just to practice the problems. I'm going to do the explanation here. The simplex method is a very, very powerful way of solving a very particular type of problem that I'm going to explain in a moment. We're going to spend a couple of days on this. And so I'm going to do the more simpler version today. So back in probably pre-calculus, maybe intermediate algebra, probably not, you had a problem of the nature. Some of you may remember this, okay? Farmer Jones plants 2 types of crops. He plants peas and corn. He's got 1,000 acres available. He makes maybe, $500 an acre for peas and $800 an acre for corn. Okay. Now, the amount of hours available to plant peas is this and corn is this, and here's how many total hours he has available. The amount of money it costs to plant the peas is this, the amount of money to plant the corn is this, and he has this much money available. You have a system of inequalities, not equalities. You have a system of inequalities, and the system of inequalities, if you graph them, again, this is baby algebra, you remember doing something like this. You had a system of inequalities, and maybe you got to picture something like this, and you figured out that your answer had to come from inside the polygon that was formed. So what you did was you found all of the vertices, and then you substituted them into whatever it was that you were maximizing or minimizing, probably the profit. You got this much dollar per acres of peas, this many dollars per acre for corn. You don't just automatically choose one of them because that may not be the best choice. Now, this concept is called linear programming. Okay, and I would hope that you did something like this in your pre-calculus classes because it's considered major stuff. The problem with linear programming is it's a system of inequalities. So there are an infinite number of points that satisfy all of the inequalities simultaneously, but an infinite number of points, there has to be a best answer. If I'm maximizing the profit, next day we'll look at how do you minimize the cost. So I first had to set up my system of inequalities, and then eventually I'll get this picture. Now, a lot of folks don't realize how important inequalities are in general. Most things in life are not equations. Most things in life, you're dealing with inequalities. And I'll give you a simple example. You're going to go to the store later on today. Okay, you got 20 bucks in your pocket, and you're going to go to the store and you're going to buy some groceries. And you get to the check stand and it's $18.50. You can't leave. You got to go back and find $1.50's worth of stuff because you have $20 and you have to spend all 20. Or would it be okay to spend less than that? No, okay. Some of you have, let's say, recently you've renewed your driver's license. And so you had to take that written test again. And every time I ask somebody, I get a different answer. But maybe it's you can miss 6 problems or something like that. So you took your driving test and you feel pretty good, but you don't think you missed any. And it says you missed 6. So now you got to go back and find 6 things and change them to wrong answers so you miss exactly 6. Or would it be okay to miss less than 6? Oh, okay. Okay, some of you kind of get that one. You operate the budget at your work and you have this much money to spend every month and you did not spend all that money. Oh gosh, I got to quickly go spend it at the end of the month, or maybe I don't. These are all inequalities. And the most painful one, I always hesitate to bring this one up because there's a lot of pain and suffering for some of you. Okay, you're in junior high school. Okay, junior high school, you're probably 13 years old, maybe 14. Junior high school, and you're with maybe some group, some youth group, some club or something, and you're going to the amusement park. Now, the young ladies, you don't relate to this one at all because you were full grown at 13. The guys, a lot of late bloomers in this room, and you guys remember, you can't ride the ride. Remember the evil cardboard clown? You guys remember that? You can't ride the ride unless what? Anybody? Remember the evil cardboard clown's probably about this tall? You can't ride the ride unless
You're so tall.
you're this tall, and you weren't, and you couldn't ride the ride. Oh yeah, Legoland, they have some fancy roller coaster-ish ride, and my oldest son went to Legoland several times, and he was never tall enough to ride that ride. He was so sad. All of his friends would be riding it. He was the shortest kid in his class. So what he did is he got newspaper. He got an entire newspaper. He wadded up the newspaper and put it in his shoes. Lots of newspaper. And it gave him about an extra inch by doing this. And like his 4th try, he finally rode the ride. He was tall enough. But that evil clown, a lot of you remember, you had to be this tall. But what if you're taller than the clown? Does that mean you can't ride the ride, or do you have to stoop down? No, again, inequality. And there's words that we use. When you went to the grocery store with $20, you can spend at most $20. You can't spend more, but you could spend less. You've got to be at least as tall as the clown. You can be taller, but you can't be shorter. Anything with money, we realize this, okay? When we play a basketball game, we must win by exactly 1 point. Well, we can win by more than 1 point. Most everything is an inequality. And when we have systems of equations, we know exactly how to solve that. We can use matrices if it's linear equations. But what if it's linear inequalities? Problem is we can't use a matrix because there's an infinite number of solutions. So this is what I'm going to show you today. It's something called the simplex method. So what I'm going to do is I'm going to do a simple problem the old-fashioned way, just so you can see what it looks like and see what the answer is. Then I'm going to show you the simplex method for that problem. And it's kind of neat. So think of the peas and corn and all that example. And what ends up happening is, here's what I want to do. All right. I want to maximize, let's say, the profit of 8x plus 10y. And we write it this way. Subject to x and y are non-negative. So think peas and corn. I can't have a negative number of crops. X plus 3y is less than or equal to 48. X plus y is less than or equal to 26. 4x plus y is less than or equal to 80. Okay, now there's multiple sets of inequalities that this picture produces. So I'm going to go through and I'm going to draw you a rough sketch of what it is you're finding here. Hopefully you guys can all, yeah, that'll work. So my lines will look something like this. So I'll always start by drawing the lines, the equals. And my equals will be, hold on, that one is going to be, and then I've got one. And then the last one will be about, okay, it's not a perfect picture, but it's kind of ish. All right, again, not a great picture. So let's say this is the line x plus y equals 26. Let's say this is the line, has the steepest slope, 4x plus y equals 80. And let's say, what's the other one? Oh, there it is. Oh, I'm sorry. No, wrong one. That would be this line. Sorry. This is x plus y equals 26. This one here would be the x plus 3y equals 40. There we go. Had the smallest slope. Now, the x and y both being greater than or equal to 0 means I'm entirely in the first quadrant. So clearly, this is my region right here. I clearly have 5 points of intersection. Now, again, don't go by the accuracy of my picture. It's pretty terrible. I can do circles and draw spheres. I can't draw line segments. I need to find these intercepts. Okay. Now, I made it so all of them are fairly simple to find. Now, I'm going to explain the theory because there's a lot of calculus involved in the theory that you're never told in baby algebra. All right. So this point here is 0, 16. This is obviously the origin. So 0, 0. This point here is 20, 0. This point here is 18, 8. I'm saving you a little time and trouble. And this point here is 15, 11. All right. So what I did was I set the equals. I solved this system, I solved this system, and then I solved this system, and that gave me these points here. Okay. Some of these points on this picture. So, by the way, this one here, not relevant because it's outside the region entirely. My answer must come from one of the vertices. Now that's the part in linear programming, they never explain that. My region clearly has an infinite number of ordered pairs, all of which satisfy all of these. Every ordered pair within the region or on the boundaries satisfies every inequality because they're or equals. So why do I only look at the vertices? This is a calculus problem. Now think Calc 1 for a moment. We'll keep it really, really simple. You remember optimization. I want to maximize or minimize something, I might have some constraints. So what you did was, and by the way, this is also, we do this in Calc 3, right, in 3-dimensional sense. If I want to maximize or minimize something, the first thing I do is I take a derivative, I set it equal to 0, and then I find the x values, right? Those are called the critical values. Now, what if you had a closed interval, then you could use what's called extreme value theorem, which says that if you have a closed interval, then the maximum and minimum absolutely come from either the critical values or the endpoints. Okay, that's Calc 1. Notice that I have closed intervals. I have this line segment, I have this line segment, and so on. I have closed intervals. So that means that if I have closed intervals, then the answers must come from critical values or endpoints. But lines do not have critical values. Because if I differentiate a line, I get a constant. I can never set the derivative of a line equal to 0. No line has a critical value. Oh, so according to the extreme value theorem, if my maxes and mins must come from endpoints or critical values, and there are no critical values, what do you got? Then all of your maxes and mins come from the endpoints. Now in Calc 3, we do this with regions, if you remember. We have an infinite. Okay, and so we take the derivatives that equals 0, we use the Hessian matrix, we do all this stuff, and we find where the maxes and mins can occur. But if you have a bounded region, then you also had to look at the boundaries. It's the same thing. I have a bounded region. if I do not get a critical value inside the region, then the maxes and mins must come from the boundaries themselves. That's absolute, that's calculus. We're not using calculus in this problem, but that's the justification that says the answers can only come from these vertices because they're endpoints of intervals. Okay, so I'll leave it at that. In linear programming and baby algebra, you were told to just look at the vertices, but not told why, because it was a calculus argument. So what we do is we're going to write down each ordered pair, 0, 0, 0, 16, 15, 11. Hopefully I can fit these all in here. I'll increase this a little bit. 18, 8, and 20, 0. And we're going to calculate what the profit would be on each one of these. Okay, so at 0, 0, let's see. If I put X and Y as 0, I'm pretty sure I get 0. All right. 0, 16, I think I'm going to get 160. At 15, 11, times 8 plus, I'm going to get 230. At 18, 8, so 8 times 18, I'm going to get 224. And at 20, 0, I'll get 160. So which scenario maximized the profit? Looks like this one. Okay, so the maximum profit will occur when X is 15 and Y is 11. Now, what if I change these coefficients? What if I increase or decrease the X coefficient, or the same thing for the Y? Well, then all of these values would change and my best case scenario might come from a different place. Okay, I could, for example, what if I made the X coefficient huge compared to the Y coefficient? Then that might be the best. And what if I made the Y coefficient huge compared to the X coefficient? Well, then maybe that one's the best. So it doesn't matter which one you choose. You just choose the one that this is maximized by, which could be any of these. Worst case scenario is I didn't produce anything. So that was 0. So this is the basic baby algebra approach. And notice that the answer came from 15, 11, and the profit was 230. I want you to remember that because I got to erase all this. Now I'm going to walk you through the simplex method. And I'm going to do it for this problem because we already know the answer. That's key. When we do this in general, it's going to be bigger problems. Now you'd say, why would I need a separate method if I can do this way? In fact, I didn't even have to draw the picture. I just had to find the vertices. You're correct. But what if I had a system of inequalities with more than 2 variables? Oh, they wouldn't be lines on a plane. They'd be planes in 3 dimensions. What if I had a system of equations with more than 3 variables? Now I'm in 4-dimensional space and I can't draw that. I can't find those. No, that would be impossible. I'm doing this problem because it's short enough and simple enough for us to interpret. So now let's go back. I want to maximize. I'm going to redo the problem, but now we're going to do it using the simplex method. 8x plus 10, P equals 8x plus 10y, subject to, I need all the space here. X and y are greater than or equal to 0. X plus 3y is less than or equal to 48. X plus y is less than or equal to 26. And 4x plus y is less than or equal to 80. Now, I cannot solve a system of inequalities using a matrix, but I can make a system of equations. Because this is a less than or equal, there potentially is a variable that when added, or just say a value that when added to the left side would make it equal. So what if I did this? X plus 3y plus S1 equals 48. Now, S1 could be 0, S1 could be positive, S1 cannot be negative. X plus y plus S2 equals 26. 4x plus y plus S3 equals 80. The S's are called slack variables. They're the variables that basically take up the slack. Now, in the case where I was talking about Farmer Jones and the crops and all that kind of stuff, is it necessary that I used up every acre or every dollar or every hour of labor? Maybe not. Maybe I've produced everything I can and I still have money left on the table. I still have hours of labor left. It's quite possible that you do not use up all of your resources. It's very possible. In fact, the more variables I have, the more inequalities I have, the more likely I'm not going to use up all of my resources. So the slack variable would be kind of like the unused resource. So whatever that represented, that's kind of a generic big picture view. Now, the last thing I'm going to do is I'm going to rewrite this as negative 8x, negative 10y plus p equals 0. And we're going to create a matrix from the system of equalities now, okay? So the matrix will look like this. The first column will be the x's. 1, 1, 4, negative 8. Second column, the y's. 3, 1, 1, negative 10. The next column, the S1s. Well, there's only the 1. Then the S2s. Well, there's only the 1. Then the S3s. There's only the 1. And then the last column, there's not going to be a separate variable for the p, because this value here will end up being the p every time. So the last one's going to be those constants. This is the matrix. Now, what's different is I am not going to solve this in the same way we did before. We do not go for Jordan canonical form. We do not go even for row echelon form. We have a completely different goal in mind. Now, the theory behind the simplex method, I was confused even in grad school. It's very, very, very theoretical, okay? I'm showing you the practical. So what we do is we have to choose our pivot. Our pivot is not necessarily in the upper left. And here's how we choose our pivot. On the bottom row, we start with the largest negative value, which would be the negative 10. So the pivot will come from this column. The pivot will either be this value, or this value. So the first thing is the pivot's got to be a positive value. How I choose my pivot now, I take the ratio of 48 over 3, I'll write it down. I take the ratio of 26 over 1. I take the ratio of 80 over 1. I take the ratio of this value over this value for everything in that column. Whichever one of these is the smallest positive value. I just said a pivot cannot be negative in this context. The smallest positive value will become our pivot. That's 80, that's 26, that's 16. So it's clearly this guy. So our pivot will come from that value right there, because 48 over 3 gave me the smallest positive value. So I start by looking at the bottom row, choosing the largest negative value. I then go, which one has the smallest positive ratio? Now, we're going to begin the process. As long as there are negatives on the bottom row, you are not finished. You're only finished when there's no more negatives. Now, here's an interesting thing. You remember we had 5 vertices. That means all 5 of those answers are viable solutions. That doesn't mean they are the answer, but all of them could work. The way we know we're done with the problem, I just said, is when all of these are negative. But the other thing is the answer can only—
Sorry for that to interrupt, Mr. Brown.
Yeah.
On the columns over there, so the 4th, the 5th column, so those ones represents which letters? I'm sorry.
The slack variables.
Okay, so we have X and Y, and then it's S.
X and Y and S1, S2, and S3.
X1, X2, and S3.
Those are your only variables. P is not a variable. X and Y are variables. P is just a result. Just like that's a constant. We actually think of P as being a constant in that case. And right now, here's where you read your answer from. I'm going to go through this each step of the way. These 3 columns are called unit columns because there's a 1 and all the rest are 0, kind of like a unit vector. Those are called unit columns. Your results can only come from unit columns. And your result would be read, S1 is equal to 48, S2 is equal to 26, S3 is equal to 80. That would mean I didn't use any X's and Y's. That's a bad answer, but that's what 0, 0 would represent. 0, 0 means I didn't use anything. Not a good answer, but it actually would agree with my matrix. So we start the problem. I take my pivot and I'm going to make this a unit column. So the first thing I need to do is I have to make my pivot into a 1. So our first step is 1/3 row 1. Okay, the pivot has to be a 1 because I have to have a unit column. So this is going to be 1/3 1, 1/3 0, 0, 16. You just multiplied that row by 1/3. And then everything else is staying exactly the same. You're not changing anything because you're not doing anything yet. And then 0, 0, 0, 1, 0, 0, 0, 1, 0. Oh, here we go. 26, 80, 0. All right. What I like to do when I select my pivot, I always like to circle it so I don't forget where I am. Now I'm going to put zeros below that value. Okay. I'm going to put zeros below that. Now I'm going to have to write kind of small to get everything on here. So I'm going to take negative row 1. I'm going to add it to row 2. Negative row 1, when added to row 2, I'll get a 2/3 there, a 0 there, a negative 1/3 there, 0, 1. Whoops, did I lose a column? No. 0, 1. The negative of this plus that negative. Oh, here we go. Sorry, got it backwards. 1, 0. And then the negative of this plus this would be a 10. Okay, because that's a 16 right there. Then I'm going to take negative this and add it to this row. So negative 1/3 plus 4, that's going to be 11/3, then 0, then negative 1/3, then 0, then 1, then 64. And finally, I'm going to take 10 of these and add it to here. So 10/3 plus negative 8 would be negative 14/3. And then 0, and then 10/3, and then 0, then 0, then 160. Okay,
Professor?
so I did negative, hold on, I did negative this plus this, that's arithmetic, negative this plus this, 10 of these plus this to produce a unit column. The numbers are just whatever they are. Yes. I'm just not writing that row operation.
Never mind.
Compromise for space theory. Everybody okay? So if I stopped now, I'm not done, but if I stop now, only the unit columns can produce a viable solution. The first column is not a unit column. What that would mean is that the X variable would still be 0, but notice the second column, which is the Y column, says, hey, the Y value could be 16. The X value would be 0, the Y value would be 16, and my profit would be 160. If you go back to what we did before, this was one of our results, wasn't it? 0, 0, profit 0 was a result. 0, 16, profit is 160 was one of the possible results. And that would be red. And notice in this case, the slack 2 and the slack 3 would mean I still have a bunch of unused stuff. So if I go up to here, 0, 16, I used all of this resource, slack 1 would be 0. 0, 16, I still have 10 whatever's left over. 0 plus 16 plus S3, S3 would be 64 unused portions. Right here. That's not my final answer because I still have a negative on the bottom row, but every round, every time I produce a unit column, what you have in front of you is a viable solution from the graph that I drew. It's one of the vertices. It's not my final answer because I'm not done. So the next step is to produce the next pivot. So I only have one negative, it's right there. 16 over 1/3, that's 48. 10 over 2/3, that's 15. 64 over 11/3, that's bigger than 15. So my pivot is going to come from here. Again, that quotient was 48, that quotient was 15, that quotient's like, I don't know, more than 15. Like 17 or something. I need to make that a 1, so I'm going to do 3/2 row 2. So 1/3, 1, 1/3, 0, 0, 16. 1, I'm multiplying this row by 3/2. So 1, 0, negative 1/2. 3/2, 0, 15. And then I just repeat the last two. Like I said, normally I would have lots and lots of room. Now, this will probably be the last step of the problem. If for some crazy reason, when I'm done with this step, if I still have a negative on the bottom row somewhere else, I have to deal with that. You're not done until there are no negatives on the bottom row. When I do this to get rid of that guy, I should not be introducing any negatives. That would probably be an error. Okay, so I'm going to say it, but I don't really have room to write these steps. So this is 1, 0, negative a half, 3 halves, 0, 15. All right, I need to take negative a third of this and add it to here. Negative a third of this, that'd be 1/6. Added to here would be 1/2. Negative a third of this, that'd be negative a half added. 0. Negative a third would be negative 5. Added to this would be 11. Okay. Negative 11 thirds added to here would be 0. Negative 11 thirds, went ahead and did it so we didn't have to think too much. That's going to be, hold on a second, 3 halves. Because I'd be positive 11/6 minus a third. Negative 11 thirds added to this, that'd just simply be negative 11 halves. That's still a 1. Negative 11 thirds added to here. So negative 11 thirds would be negative 55 plus 64 would be 9. Now finally, 14 thirds of these added to here, that's 0. That's 0. 14 thirds, that'd be negative 7. Does that sound right? Sorry, negative 14 thirds, sorry. That'd be 7 thirds. Negative 7 thirds, 14 thirds added to here would be 1. 14 thirds, that's 7. 0. 14 thirds, that would be 70, plus here is 230. Okay. First thing, notice, no negatives on the bottom row. That means we're completely finished. There is no more work to perform. Now it's just reading our answer. How do I read my answer? I go
Professor,
to the, yes.
what was the last operation you did for that final matrix?
Well, that's my pivot. So I'm putting 0, negative a third of these plus this, negative 11 thirds of these plus this, positive 14 thirds of this plus this. So whatever it takes to put the zeros, right? And then we just carry it all the way through, remember. Now, answers can only come from unit columns. Here's a unit column. Here's a unit column. Here's a unit column. What does this say? It says that X is 15. It says that Y is 11. And it says the profit is 230. Does that sound familiar to anybody? Is that exactly the answer we got when we drew the picture and did it that way? Yeah, it's exactly the answer we got doing it the other way. Well, that's kind of cool. Now, finally, how do I read this? Well, according to this, okay, remember I have different restrictions along the way. If X is 15 and Y is 11, 15 plus 3 times 11 is in fact 48. I don't have any S1 left over. I used all of that resource. 15 plus 11 is 26. I used all of that resource. 4 times 15 plus 11, that's 71. Okay, if that's 71, that means whatever this resource was, there was 9 of it left over. That could be money, it could be time, it could be whatever. And notice, now I do not include the slack variable in my answer for the simple reason my only variables are X and Y. I'm trying to say how much should each one be. Now understand, I mentioned before, we have certain restraints or constraints, I'm sorry. So we have this much money to spend. We have this amount of time to spend. Maybe I have this much labor to use. I don't necessarily use all of my resources. I just can't exceed any of them. So whatever all my resources are, there was one resource that wasn't completely used up. Okay, that's perfect. This is my final answer. You can express it like this because this isn't necessarily a point in space. I'm solving a problem saying X represents, you know, maybe in this case it was acres of peas and Y is acres of corn or something like that. Okay. Now, I mentioned before, if I change the coefficients on here, every aspect of this problem changes and the solution clearly changes. I'm doing the problem. This is a very simple point of view because I was able to clearly draw a picture that represented this. We found the answer the old-fashioned way, the baby algebra way. And now we see the simplex method produce the same answer. What we're going to do next day is do a bigger problem, a problem with more variables. It's not possible to draw that problem unless you have some kind of holographic image that can draw planes and, you know, boxed regions. That one you can't actually do from a viewing point. This case, you're going to do the same thing, and we're going to be able to solve the problem from beginning to end. It's kind of cool. Now, on the posted notes, I've got some simplex stuff where I walk you through a problem from beginning to end. It's kind of the same thing. I think that's a 3-variable problem in that case, because that's what we're really going to be looking for in general. Okay, so I'm going to stop recording now.